I've sorted it out now. Right, okay. Right, so thank you everyone for joining us for this session. This is our third session for this theme, November theme, which is Earth and Solar Systems theme. And again, today we have got a scientist from University of Oxford, Dr. James Bryson, who is a planetary scientist at the Department of Earth Sciences, as I mentioned, at the University of Oxford. So in our live discussion session today, we are going to have a 30 minutes session where we will be going through some questions with James. And after that point, we will then start a break for 10 minutes. And after that break, we will be coming back to actually ask your questions on your behalf to James. So James, I would like to thank you for sparing your time for us today. It's an absolute pleasure to have you here. And I think I would like to start by asking you about, giving us a brief introduction about yourself, if that's all right.
Hi, and thank you for having me. So I'm James Bryson. I'm the Associate Professor of Mineralogy here in the Department of Earth Sciences at the University of Oxford. And I study how our solar system transitioned from a colossal chaotic disk of dust and gas into an organized collection of planetary bodies, which is the very first set of processes that occurred in our solar system that allowed us to form anything that could support any type of habitable life. And I do that mostly by looking at the samples that actually date from that time period, date from the first few million years of the solar system, which we have on Earth today in a variety of forms of meteorites.
Great, thank you. So before we actually start going through more in-depth, questions, would you like to tell us about, what is a meteorite, what is an astrocyte, or any other object, extraterrestrial object that you think might be useful for our discussion?
Sure. So very early on in the solar system, the first solid objects formed, which were smaller than a millimeter. And then those started clumping together to form objects that were a meter size. And then those started clumping together to start forming things that were kilometers to hundreds of kilometers big. And those objects that are about 1 to 100 or so kilometers still exist today in the solar system as asteroids and comets. So the asteroids and comets are sort of remnants of that very early planetary formation stage. And asteroids form comparatively close to the sun, where the temperatures just from heating from the sun are slightly higher, and comets originate from further away from the sun, where temperatures were lower. So they contain things like ice and other phases that are only stable at low temperature. And if any of these planetary objects in the 4.5 billion years since they formed undergo any sort of collision or impact event, small fragments get broken off, and those fragments are gravitationally unstable within the solar system. And in that case, they start spiraling into the sun. And if they happen to be on an orbit that coincides with the Earth's orbit, they fall to Earth in the form of a meteorite. So a meteorite is just a fragment of any other planetary body, and most meteorites originate from asteroids which are in the asteroid belt, which is between Mars and Jupiter.
Thank you. So obviously these objects do move quite a lot. So, would you like to tell us a bit more about, how that movement is actually manifested? How does it happen?
So it's all a result of gravity. So you have the Earth, Mars, and the asteroid belt, and then Jupiter, and they're all in stable orbits around the sun. But every time the asteroids orbit, they all gravitationally interact with each other. And every so often, they just slightly change each other's orbits. And then somewhat fortunately, within the asteroid belt, there are two really unstable regions. And if an asteroid is perturbed on its orbit, such that it ends up in one of those two regions, it really strongly gravitationally interacts with Jupiter. And in that case, it gets thrown out of the asteroid belt. And in that sense, it can then start hitting other things and colliding and fragmenting, and then those fragments start spiraling in towards the sun. So most of the motion is due to gravitational interactions. Some of it is due to interactions with light from the sun as well, which can move objects on longer timescales.
Okay, all right. Thank you. So where do these objects actually do come from, though? We know from our previous talks within this themed month that they do form, like you say, around Jupiter. So, where do they actually come from? We know that some of them might be already happening to be there because they couldn't form into a planet, but where do they originate from?
That's a really good question, and ultimately the two properties that dictate how any planet forms and evolves are where and when its constituents formed. So where these things come from is a big open question, and the when we've been able to address for decades using measurements in the lab. The where is actually a much more difficult question to try and probe. We can observe some meteorites using telescopes coming from the asteroid belt. So we know a lot of them come from there, but sort of a question before that is, were there asteroid-sized bodies distributed uniformly throughout the solar system, and then some of them happened to coalesce into the planets we recognize today, and the asteroid belt was lucky and that got left alone? Or is that a localized region of the solar system where this happened to be, where small planetary bodies happen to be forming more? It's something that we are actively looking into at the moment, and a lot of my research is trying to answer that question of where do asteroids form and where do meteorites come from?
Okay, thank you. So, so how do we actually know where these objects are actually coming from? What type? You mentioned you do some research around this field, but how do you know where an object is coming from? How do you find out where is their place of our origin?
So the least ambiguous way of doing so is just following it with a telescope, but we have very few of those. I think there are about 20 meteorites that we've been able to trace back their origins to the asteroid belt explicitly. What I do is I study the magnetism of meteorites. So when meteorites were forming billions of years ago, there could have been magnetic fields present in the solar system that aren't present today. And most rocks, when they experience a magnetic field when they're forming, remember that magnetic field. Just like a hard drive remembers your information stored in its magnetism, rocks do the same thing. And that magnetic field, if it was present at the time, was actually supported by the protoplanetary disk itself. And the protoplanetary disk is this huge cloud of dust and gas that surrounded the young sun. And that field that it supported was strong near the sun and weak far away. So what we can do is we can measure the magnetism of particularly ancient meteorites and say it's got a magnetic field intensity of whatever value that we measure. Then we can compare that to how models of the protoplanetary disk predict the magnetic field should have varied. And we can do that comparison and say this matches if we think it comes from around where the asteroid belt is today. So that's actively where a lot of my research is going at the moment. But there are a number of other people working on this problem from a different point of view using different techniques. So the isotopic composition of meteorites. So just the ratios of the different stable isotopes of the elements, that can tell you about where meteorites come from in the solar system as well.
Okay, great, thank you. So you mentioned about measuring how much magnetic field they actually do have. So what kind of techniques do you use to study, measure that type of thing? It seems a bit hard to imagine what type of techniques or methods you're using. Can you tell us a bit?
So there's three that I've adopted in my research so far. So there's something that we call bulk magnetometry. And that basically just means we take a rock and we put it in a magnetometer, and a magnetometer is just a big instrument that can measure how strong the magnetization of a sample is. We then do lots of different types of measurements on those. So we end up sequentially removing the magnetization carried by one of these samples, and how it is lost is the opposite of how it was gained. So we can learn a lot about how these meteorites and just rocks in general actually acquired their magnetization. That can tell us a lot about their history. And that's technique has been around for sort of 50, 60, 70 years now, this idea of just taking bulk rocks and measuring the magnetization. Trying to push things forward quite often, just due to how they formed and what they're made of. A lot of rocks just don't like carrying magnetic information, in the same way that there's a lot of research going into how hard drives store information, and you don't want them to have the wrong chemistry and the wrong structure. Some rocks just have the wrong chemistry and the wrong structure, so their bulk measurements are really difficult to interpret. But within those rocks, on very small length scales, there can be reliable regions that can record magnetization and pass that information on in an accurate way. And these are high resolution techniques, so high spatial resolution. And I pioneered one of those during my PhD, which involved a synchrotron, which is a very bright X-ray source. And there's one of them in Oxfordshire. And what we did there was we actually physically imaged the magnetization on sub-micrometer length scales inside these meteorites, and focusing in just on the things that we knew were reliable recorders. And that allowed us to just not pay attention to everything else that was detrimentally affecting our signal, and just focus on the thing that we knew was accurate. So that was where my research was going sort of 5 to 10 years ago. Moving forward, we're trying to bring this high resolution approach into the laboratory so we can do it much more regularly than we're able to do synchrotron experiments. We can't get to the same very high resolution, so we can't get sub-micrometer, but we can get sub-millimeter. And that's sort of the length scale of individual crystals that make up rocks. And again, some crystals have got the right history and the right structure and the right chemistry to be reliable, and others don't. So by doing this, we can take just specific crystals that look like they're going to tell us useful information and just measure those in isolation. And this opens up a wide range of new samples to reliable study as well. So it's sort of those three combined techniques that my research is adopting at the moment, and specifically moving towards the higher resolution, because it's opening up a whole new type of sample to reliable measurement. So we're getting a lot of new information using those.
Okay, thank you. That's very interesting. Thanks a lot. So one other question that I was wondering, though, we talked about obviously meteorites, asteroids and comets. So how often these things do hit our planet? Do we know from the research or the knowledge that we have so far?
Yeah, so we have pretty good coverage of when things enter the atmosphere, because obviously if you've seen any number of Hollywood movies, it can be a really energetic event. And obviously mass extinctions around the Earth have been linked to these events in the past. Just to be absolutely clear, there is nothing big heading towards the Earth at the moment. But in terms of rocks that are bigger than about 50 grams, we're gaining about 16,000 kilograms of material a year. So that's more than 320 entries into the atmosphere every year. So that's about 100 a day that have more than 50 grams. On top of that, we have a huge amount of dust falling into the Earth. And dust is sort of anything that's on the sub-millimeter length scale. And it's just floating through space and it gets gravitationally attracted towards us. And that's it's tens of tons extra material a year. So the Earth is being constantly bombarded just by things that are on the kilogram weight scale, not billions of kilograms that asteroids are. We're not going to be hit by anything that big in the near future.
All right, thank you. So I would like to move on to your introductory video, though. In there, you mentioned that Saturn and Jupiter play a role in scattering asteroids around the solar system. So how do they actually do this? We know that obviously there is, with what you said now, that magnetism obviously plays a role in the movement of these objects, but why is it just these two planets that keeps coming up for scattering asteroids, and how does it happen?
So that's a really interesting question and a very active area of research. And it all started about 10 years ago when some researchers who were trying to model how you can form the terrestrial planets, so Mercury, Venus, Earth, and Mars, and they kept struggling to explain Mars's comparatively low mass. So their models basically said you should have more massive planets the further away you go from the sun. So Mercury, Venus, and Earth matched that trend, but Mars didn't. And one way they found that they could get that result to work was basically truncating the region in which these planets formed. So we knew that we have the sun here and then Jupiter here. If you just let that distance form planets in these simulations, you didn't get the right mass trends. But if you did this and you just made that region smaller, you did get the right trends. And this was sort of a result that didn't really have a physical explanation. We know the distance between the sun and Jupiter, so we know the distance or the region in which these planets should be forming. But this was the result, that if you made it smaller, it worked, which then posed the question, how can we make that region smaller? And this was also around the time that a lot of planetary systems were being found around other stars, which have got completely different architectures to our own. So we have 4 terrestrial planets and then 4 gas giants, whereas a lot of these exoplanetary systems have got one big terrestrial planet near the sun. Some of them just have one gas giant right next to the sun, and they look completely different to ours. So that community was trying to figure out, if we know that we have gas giants that form far away, how can that gas giant then be found next to the sun? And that prompted people to think about how planets can move around inside a solar system due to gravitational interactions. And that led people to think about the history of our solar system. And they basically proposed about 10 years ago that if you have the sun here and Jupiter here, if Jupiter were to just move inwards, that would truncate the inner region of the disk, allowing the right size of planets to form. You then have the obvious issue that Jupiter isn't where we find it today, and that's something we know very well. And one way of reconciling that is actually to allow Saturn to do the same thing. If Jupiter just moves, it will keep going inwards until it hits a limit. Whereas if Saturn comes in, due to the way it interacts with the protoplanetary disk itself, it actually halts Jupiter's motion, and then they both can move back outwards. So it's this idea that due to the actual gas and dust in the disk itself, planets can actually move around, and it can explain lots of the things we see in exoplanetary systems as well. And I should caveat all that by saying that although this research was published about 10 years ago, more recent studies that have come out in the last sort of 3 or 4 years propose that simply just growing Jupiter could have had the same effect and can still create the mass distributions that we see in the inner solar system as well. So this is, again, as I said, a very active area of research, and different people are trying out different hypotheses and thinking, what if we have a combined growth migration model? Can we start explaining other properties? And some people have said, we actually get the absolute best fits to our data if we have a 5th gas giant somewhere between Saturn and Uranus. And their models even predict that that gas giant should have been flung out of the solar system, so we wouldn't see it today, and does actually explain some of the nuances in what we see in how the planets are orbiting. So lots of different people are working this from an astronomical point of view. But what this does to the architecture of our solar system is effectively, if you're a small planetary object, so if you're an asteroid and you've got Jupiter, which is huge, moving around, Jupiter completely dominates your gravity. So all of the asteroids basically get flung around all over the place. And one of the other appealing outcomes of these models is that they create an asteroid belt, and they create it in the right place with the right mass distribution and the right chemical distribution as well. So this is something that we as meteoriticists sort of gravitated towards, because we are studying samples that come from that region of the solar system. And some really interesting recent observations suggest that we actually have fundamentally 2 families of meteorites, some that originate from inside Jupiter and some that originate from outside Jupiter. But we can see both types coming from the same part of the solar system today from telescope observations. So it looks like something in the solar system allowed two distinct families to form and then mixed them. And that's exactly what Jupiter and its migration or its growth or combined growth migration should have done. Just because we have to, the astrophysicists are doing these models and then making these predictions, and then it takes us some time to do the measurements and think about what we need to measure. We're just starting the last 2 or 3 years to really try and address this problem from a meteoritics point of view. We essentially asked ourselves, if the entire solar system is being rearranged, we should be able to see evidence of that in meteorites. So we're looking for it now. And I had 2 papers come out earlier this year that seem to back up that hypothesis.
Thank you. That's very interesting. And that actually helps me to move on to my next question. I was wanting to discuss about your publications. So can you, in layman's terms, tell us about the how did your publications advance the field and help other scientists? How is it helping us to advance the knowledge? Can you tell us a bit about your research?
Sure. So those models that I was just predicting, they say that we should have small bodies that form just outside Jupiter mixing with small bodies that form just inside Jupiter to create an asteroid belt. They also say that some comet-like bodies that formed beyond the orbit of Neptune should also have been introduced to the asteroid belt. So there should be some comets in the asteroid belt due to this gravitational interaction. So I sort of posed myself the question in the position I had before the one I had in Oxford, the one I had in Cambridge. If we have comets in the asteroid belt, and if we have meteorites that originate from those comets, we should be able to find some evidence supporting their existence. And as I mentioned earlier, one of these things is the magnetic field. So if we had a meteorite that formed in the asteroid belt, it should have recorded 1 intensity of magnetization. If we have a meteorite that formed much further away from the sun, it should have recorded a much weaker field. So I set myself the task of first looking through published results to try and find candidates, and then measuring the magnetization of those candidates. And what I was able to find was 2 meteorites which have got magnetic field intensities that perfectly match what we'd expect for bodies that originate from the comet-forming region of the solar system rather than the asteroid-forming region. And one thing that I was able to sort of hypothesize about in these papers is, if they look like they form in the comet-forming region, but we know they came to Earth from the asteroid belt because, really fortunately, one of these meteorites is the 20 that we know come from the asteroid belt, something must have taken it from the comet-forming region, which we call the Kuiper belt, into the asteroid belt. And really the only thing that's been proposed to do that is these gravitation interactions with growing or migrating giant planets. So a lot of my research is trying to figure out at the moment how dynamic was the early solar system? How is that process of gravitation interaction mixing the solar system up? And sort of extending that to where I want to be going in sort of 10 years' time. If you form a small body really far away from the sun, it's cold and it can be rich in things like ice and organic molecules. And people have proposed comets as being the source of at least some of Earth's water. It could also potentially maybe have been the source of organic compounds and potentially a trigger for life on Earth. But one issue has always been that they formed far away and they had to get to the Earth somehow. So I'm trying to find evidence that we can have this inward migration of comets that can pollute the Earth and potentially allow it to evolve on a different pathway to how Venus and Mars have been evolving.
That's quite interesting, thank you. So before we break up for our 10-minute break, would you be, I know you touched this a little bit while you were answering my previous question, but would you be able to tell us a bit about how you're going to follow up this research? What is the next research project that you're going to do to follow up these findings?
So what I'm planning on doing next is still using the magnetization of meteorites. But we want to try and explore not so much if we have samples that come from the comet forming region. I'm still doing that, but sort of branching out. We want to try and differentiate whether where asteroids come from in the asteroid belt varied over time, or varied if they come from inside Jupiter or outside Jupiter. And that can tell us a lot about how the disk itself was evolving, the dynamics of that dust and gas, and also the actual processes that trigger planet formation. For example, if all planets they come from very similar distances, or all asteroids formed at a very similar distance away from the sun, that would actually argue that there was a specific feature in that part of the solar system that favored planetesimal formation. And these things have been proposed to exist. If they come from a range of distances, maybe these features didn't exist, or maybe they weren't as efficient as we first thought. So that's sort of where my research is going to go in the immediate future.
Lovely, thank you very much. So it has been half an hour. I kept you talking quite a lot. I'm sure you're tired. Now we're going to break for 10 minutes. And before we do so, I would like to let our audience know that in December, as you might be aware, we are not going to release any new material, and we will be preparing our material for next year. So again, we're following up the themes that has been selected by you. And please sit tight. It's actually going to be quite an exciting couple of months ahead of us. And in April, we will be having our anniversary event as well. So please keep tuned in. You will be hearing a lot from us. And now what we're going to do is we're going to have this 10 minutes break. And during this time, please feel free to drop your questions either to the chat section on the YouTube or to our other social media accounts. I will be collating these questions on your behalf, and I will be asking these when we resume back to James on your behalf. And when I'm doing this, if you come up with any additional questions, please feel free to add those into the chat as well, because I have got my phone on my left-hand side and I will be constantly checking it for additional questions. James, again, thank you very much, and see you in 10 minutes. Right. Hi, James. Are you sort of ready to start with the Q&A? Right. So I would like to start with one of the questions from our audience. I think that is quite interesting as well. So can asteroids come from outside of our solar system?
Yeah, so there was this object, and I'm not going to try and pronounce its name because I know I'm going to get it wrong, this cigar-shaped object, which appears to have flown into the solar system recently. As I was saying, I hinted to earlier, gravitational interactions can throw things out of the solar system. And if something was thrown out from a neighboring solar system, it can find its way into our own solar system. And it's something that NASA and the European Space Agency and other space agencies are actively observing and looking for, because these things could be completely different to what we expect to see, and could be, any number of, or could have any number of different properties to what we're used to. And especially if they are coming on a very different trajectory to what we're used to, they could pose a risk to Earth. So we're very much actively looking for these things, and they can come from outside the solar system. They're rare. We don't see them very often, but it certainly does happen, and they're very interesting. And just from a purely sort of scientific point of view, rather than a societal point of view, having a piece of another solar system would be absolutely amazing. If we were able to get a piece of that on Earth, we would learn an awful lot about how solar systems in general could form.
Okay, that's great. Thank you. So my next question is about something maybe a little bit out of your own niche research area. But recently we saw in the news that phosphine has been found in the clouds of Venus, which obviously was suggested that it can suggest the presence of extraterrestrial life. So what is your opinion on this? Do you have any standpoint about this?
Yeah, so Venus has got very thick acidic clouds, and a number of telescopes were used to sort of try and look into the composition of the clouds, and they found the presence of phosphine, which is this pH3 molecule. And it can form abiotically, so not through life, in a number of settings. But based on the properties of Venus, it doesn't look like any known geochemical, photochemical, or sort of any volcanic activity, anything like that doesn't appear to be able, on Venus at least, to create these. So either it's by a process we just don't know, some sort of interaction with the sun's radiation, or some sort of geochemical process that isn't happening on Earth, or something we just don't know at all, or it's created by life. And it is created pretty abundantly in life on Earth. Like, I went to a talk on this, and penguins produce an obscene amount of phosphine. So that was the kind of argument that they were using to suggest, although it could be another mechanism, a very not very likely, a very plausible mechanism, or very easy mechanism to generate phosphine is through biotic processes, so through life. So that was the argument. It was basically saying that we have this molecule which is most easily explained through our current understanding by the presence of life and creating phosphine through by biological reactions, essentially. And it was used as evidence that there could be, or there was, life on Venus at one point. Probably not penguins. I should caveat that by saying it probably wasn't penguins on Venus.
Okay, lovely, thank you. So what are you expecting to find from Ryugu? I suppose that's a object or planet. So could you share your insights on that?
Yeah, so the Japanese Space Agency sent a mission called Hayabusa 2 to the asteroid Ryugu. And I think it was March 2019, around then, they set an explosive off on the surface of Ryugu and collected some of the material from the blast site. And they're bringing it back to Earth. It's one of the, I don't know if it's one of the few sample return missions we have, and one of the few sample return missions that's bringing back sort of large pieces of an asteroid. And I think it arrives back on Earth in 6 days' time. So pretty soon. And Ryugu is a small asteroid which looks like it's fairly hydrated. So it looks like there was a fair amount of ice accreted into Ryugu. So we can hypothesize, based on the meteorite collection we have on Earth, what Ryugu might look like, because we've seen it, we've been to it now, we've got pictures, we've got spectra, we're having samples, and we can start comparing everything to what we're seeing in our collections. So we're at that really exciting stage of planetary science where we have so many predictions and so many people have been working on this for years, and I think it's literally in under a week the samples are gonna land back on Earth. To sort of just build on that, JAXA, the Japanese Space Agency, went to Ryugu at this very similar time to NASA went to Bennu, which is a very similar asteroid. Again, it's small, it looks hydrated. They look, at least from Earth, from the observations we can make through telescopes, to be very similar. But when they got there, they started noticing key differences between Ryugu and Bennu. So they look like two sides of the same coin in a way. They're both hydrated and they look broadly similar, but they definitely undergone different histories. And in that sense, the two missions combined are going to tell us so much about how water can be incorporated into these asteroids, how those asteroids evolved thermally. Their surfaces look very processed, so there were impacts that heated the surface and churned the surface up. So we're going to learn so much about how those processes can affect those planets, what they can do, or the asteroids, sorry, what they can do to their chemistry, what that means in terms of if that asteroid would hit Earth or another planet, what it would be able to deliver, and ultimately just about asteroid evolution in general. So it's a really exciting time to be in this area of research.
Fantastic. So the next question from the audience is about why do some planets form as gas giants, and do they behave differently?
So in the core of every gas giant is essentially a rocky planet. So the core of Jupiter, there is a rocky planet that's about 20 times the mass of the Earth. And as we go further away from the sun, we expect bigger and bigger rocky planets to form. And at some point during the evolution of those rocky planets, they get big enough that even the gas that's in the protoplanetary disk, this cloud of material from which the planets formed and the sun formed, they get so big that even that can't escape their gravity. And it undergoes, or the one proposed theory undergoes a sort of runaway accretion event where it sucks on some gas and gets heavier, so sucks on more gas, so it gets heavier, so sucks on more gas. So they get very big very quickly. And that's certainly what we think happens. Well, that's the current theory for Jupiter and for Saturn, that they have these cores that are essentially just big versions of Earth. And then on top of that, we've got this gaseous envelope. And NASA have the Juno mission currently at Jupiter, which is orbiting Jupiter right now, and is sending back loads of information about Jupiter's dynamics and its interior. So we're learning more and more about that core of Jupiter, what it's made of, how it formed, and its gaseous envelope, which is telling us about how it's evolved over its long history and how it formed as well. But due to their large size and due to their large fraction of gas, they do behave completely differently to the terrestrial planets, the rocky bodies. So for instance, Earth is generating a magnetic field today that makes your compass point north. And that's created by the fluid flow of molten iron inside the core of the Earth. Jupiter is also creating a magnetic field. It's being created by an entirely different process due to its high pressure. So they do act completely differently because of their sizes.
Okay, thank you. So I'm going to go back to meteorites. So how long would it take for a meteorite to travel from the Kuiper belt to Earth?
Asteroid-sized bodies or sort of fragments can travel anywhere up to about 10 kilometers a second is a reasonable number to be working on. The Kuiper belt is 14,400,000,000 kilometers away, and Earth is 150 million kilometers from the sun. So if you just take the distance and if it's moving at 10 kilometers a second, it's on the order of about 100 years, which isn't, given the age of the solar system, not that long. They can cover a good distance in a fairly short amount of time.
Okay, great. And, I've asked this question within this themed month as well, but I would like to get your sort of personal expert opinion on this as well. If it's taking that much time for a meteorite to travel from the Kuiper belt to Earth, how do we know that when they arrive actually to Earth, that they are what they were 100 years ago?
That's a really good question, especially with things that come from that far away. Earth is relatively close to the sun. So if we just bring something that's never experienced a high temperature, like a comet, that close to the sun, phases that were stable at low temperature will stop being stable. So it was a really interesting paper that came out over the summer that was studying a comet, and they found the presence of ammonia and lots of volatile phases, so organic molecules and ice inside the comet. But we also have samples of that comet from a NASA mission, and they don't contain those molecules. And an almost inescapable explanation is that those objects are at room temperature. So any ice isn't stable at room temperature. That ammonia isn't stable at room temperature. So simply just by moving in and becoming hotter, we start affecting these objects as well. But unfortunately, from an analysis point of view, it's very difficult for us not to do that. There are some really interesting meteorites. So some of them fall in Antarctica, which allows them to be preserved at low temperature. But getting them from Antarctica to a storage facility and then distributing them to researchers is difficult, keeping them at that temperature. There was one meteorite that fell in 2000 in January in Canada and fell into a frozen lake. And the researchers picked up pieces from the lake and from the areas around the lake, but they also took out drill cores of like ice cores with meteorite embedded in it and have kept it in a -80 freezer ever since. So those meteorites have never reached room temperature, or they have, if they did on their asteroids, they haven't done for a very long time since. And they're being kept under these strict conditions to ensure that we have samples that could have preserved that very, very pristine chemistry before they started heating up.
Lovely, great, thank you. I mean, it would be really, really nice to have this technology where we could just maybe travel back in time in space and get the meteorite from 100 years ago and now and compare it and see if anything has changed. And one last question, though, before we actually finalize today's session. So obviously, there might be a lot of young people out there who are aspiring to become planetary scientists. So what advice would you have for individuals who are interested in a career in this field? And could you also add into, what did inspire you to actually get into this field? That might be very helpful for young people at that stage of their life.
So planetary science is this really great community to work in, partly because of the people, but also just because it's really exploratory. We are finding new things we just didn't know every single day. For example, the biggest asteroid in the asteroid belt, Ceres. We went to Ceres a few years ago with the NASA Dawn mission, and we just discovered so much about that asteroid that we didn't know existed at all. And it was all brand new information. The New Horizons mission, which flew past Pluto, we knew essentially nothing about Pluto. And now we've got these gorgeous high resolution images showing that it's got mountain belts and it's got convecting ice fields, and it is comparatively active, especially for something that far away and cold, and it's got 4 moons. So there's just so much to discover all the time, and it's constantly evolving, and that's just a really exciting environment to be in. In terms of my background, I have always really enjoyed learning about space. I remember at school definitely finding that the most exciting part of physics. My parents will attest to this. I had a rock collection when I was like 5, which I think probably just put me on the right pathway as well. But I also kind of want to say that I don't have a physics A level. I did my undergraduate in Cambridge, but I didn't choose to do the physics courses. And my research is very physics-based now. So if at one point you feel like you've made a choice that closes a door to you, just assess all of your options. I thought at one point in my academic career that I couldn't go into space science because I don't have a physics background. But I don't think that's true. It takes a lot of hard work and a lot of determination, but you can definitely do it. So if you are interested in it, do stick with it. It is a really exciting field to be working in.
Great, lovely. Well, thanks very much, James. It has been a pleasure to have you. And I would like to thank everyone who did stay behind for the Q&A session. And I hope to see you all in our first January session in 2021. Hopefully by that time things will be improving and we will start going back to normality a little bit. Thank you.
Thank you.